All right, last lesson in chapter 2, 2.8 is called the intermediate value theorem. Okay. So, warm up thinking about what's the difference between a continuous function and a discontinuous function. So there's lots of ways to talk about it, right? One way I'm just going to simply say is that the continuous function flows through the graph with no stops, right? There's no breaks, there's no gaps, there's no jumps, there's no asymptotes, none of that stuff. So draw a continuous function that meets the following conditions. There's a ton of ways to satisfy the fact that f of 2 equals negative 3 and f of 5 equals 4. So that means we have an ordered pair at 2, negative 3 and at 5, 4, right? So I could do something very, very basic and say, oh, well, here's 2, negative 3 roughly. Here's 5, 4. And there's my graph. That was supposed to be a straight line. It's close enough to it. Or I could have something more complex. 2 points, same ones, 2, negative 3, 5, 4. And maybe I'd do something like that, right? Both of them functions. Both of them would pass the vertical line test. But there's lots of options. Intermediate value theorem will investigate these two different ideas here. Ignore that page, I'm sorry about that. Okay, so theorem 1, the intermediate value theorem states, if f of x is continuous on a closed interval from a to b, inclusive, f of a does not equal f of b, right? The y values are not the same. Then for every m between f of a and f of b, there exists at least one c value that belongs to ab, such that f of c equals m. All right, so that's super wordy and a little bit confusing. I'm just going to give you a quick graph. An m value is a y value, first of all. What they're saying is that, right, if we have those points, a comma f of a, and we have another point of b comma f of b, intermediate value theorem guarantees every moment in between. We could have a c comma m. You don't skip over any moments, you don't jump, you don't do anything that creates a break in the graph. So every y value is guaranteed by an x value from a to b. So for example, a car speeding up, right? If you're at a stop sign and you go to 50 miles an hour, you can't skip over the speed of 40 miles an hour to get there. You're going to hit every single speed along the way. Or altitude of an airplane, right? You take off from ground level. You get to your max flying altitude. The plane is not jumping from one level to the next. It's gradually getting there. The rate might change, that's fine, but you're not missing any altitudes along the way, okay? Okay, so a question could be really, really basic in this section. Prove that the equation sine of x equals 0.33 has at least one solution. Okay, so it's kind of like, oh my gosh, what do we want to do from there? Imagine that you need to do this problem without a calculator, right? Okay, so the first thing, again, we're acknowledging that we want to do this problem without a calculator. So we know that sine x is continuous on 0 to pi over 2, right? I don't have to pick anything too much larger than that, and you'll see why in a moment. Obviously sine x is continuous for more than that, but we don't need to go any larger interval than that. So that's part of IVT, right? You have a continuous function on a closed interval. Then I can show that sine of the a value, or sine of 0, well, that equals 0. And sine of pi over 2, the b value, that equals 1. Now, you might be able to see this is why I'm selecting this interval, because between 0 and 1, between my outputs, 0.3 is there. So therefore, somewhere in the closed interval 0 to 2, there must be an x value that would give us an answer, a y value of 0.3. And that's all we're stating. So the statement is this. since sine x is continuous on 0 to pi over 2, and sine of 0 equals 0, and sine pi over 2 equals 1, the IVT guarantees sine x equals 0.3 for some x in 0 to pi over 2. Okay, a couple more examples. So show that the square root of c plus the square root of c plus 2 equals 3 has a solution. Okay. Well, thinking about, what interval to go with, I want to make sure that I am larger than getting an output of 3 is my main thing. So I'll start at 0, that's fine. And I could go with 9, for example, right? Because then square root of 9 gives me a 3, and then that second one must also give me something larger than 3. I could go with 16, I could go with 25, but I want to go with some kind of a perfect square. So I'm going to go with 9 for that matter, because that's the first value that would satisfy this solution. So there's my closed interval. I know that I'm continuous on that interval. I don't have any domain restrictions. I can show that square root of 0 plus square root of 0 plus 2 is equal to the square root of 2. And the square root of 9 plus the square root of 9 plus 2 is equal to 3 plus square root 11. And then I would just make the statement that 3 is greater than square root of 2, which is less than 3 plus square root of 11. Okay, so the next one. Thinking about values that would satisfy the closed interval and then give us an answer in this. So for me, it was a little bit easier for something like this to put it set equal to 0. Okay. And then I decided, well, if I need something that is going to be greater than 0 and less than 0, I might want to pick positive and negative exponents in order to get this closed interval. So I'm going to go with a -1 up until a 2. I think that's probably the hardest part of these problems, is finding that closed interval that will end up satisfying what we need. So sometimes you have to play around with it, a little bit of guess and check, and sometimes logic will get you there right away. So 2 to the negative first plus 3 to the negative first minus 4 to the negative first is equal to a half plus a third minus a fourth, which comes out to be 7/12. So 7/12 is larger than 0. So now the other solution, 2 squared plus 3 squared minus 4 squared, 4 plus 9 minus 16, is smaller than 0, which is what we needed. So 0 falls between 7/12 and -3. So in both of these cases, I'm sorry, I forgot to summarize the last one, IVT guarantees a solution in 0 to 25 because of the fact that it's continuous on that interval, right? And we have our function values. Okay. Same idea here. So IVT guarantees. So I'm okay with you doing the shorthand as long as you're showing me the work proving the other steps. The solution in -1 to 2. Okay. Okay. So that's what the intermediate value theorem does. It guarantees that there is a y value. Maybe you can't solve for it. Maybe you don't know exactly what the corresponding x value is, but you know that that solution is going to exist. There will be problems throughout the year that's all you need to be able to state that, yeah, it's there. I'm not sure exactly what the answer is. I can't solve it algebraically, but it has to exist because we meet this value that's lower than it, and we meet this value that's higher than it, and my function is continuous between those two values, so I know that I have to hit it. Okay. All right, so that's the end of chapter 2. Congratulations. One down, and depending on the section that you're in, lots more to go. But either way, good job.